Hello everyone, I hope you'll be all good. So in this video we have to discuss about the new topic, that is sound. So this is topic number 3.4 in the topic of waves. So we have to discuss about the sound waves. Let me just connect it. Okay, so let's start off. So first of all, we'll discuss how the sound is produced. So remember that the sound is produced. Let me just write down the question: how the sound is produced. So the sound is produced due to some vibration. If a source vibrates, it produces the compressions and rarefactions. It disturbs the air particles, and when the air particles are disturbed, sound is produced. All right, so sound is produced by a vibrating source. By a vibrating source. When a source vibrates, it disturbs the particles, no matter whether it's solid, liquid, or gases. So when the particles are disturbed, they travel from one point to another, and due to which the sound is produced. For example, we have some air particles here. These are the random air particles. Here you go. And let's suppose we just put a speaker over here like that, and we turn on the switch of the speaker. So what happens is you will see a disturbance in these air particles. So these air particles will be vibrating from their position. They will get disturbed. So in this way, the sound will travel from this point to that point. All right, and the disturbed particles will look like this. You'll see some particles close to each other, and you'll see some particles away from each other. Again, some particles close to each other, some particles away from each other, close to each other, away from each other. Now you see the particles over here that are close to each other, and these are the particles that are away from each other. So the particles that are close to each other, we will call them compressions, and the particles that are away from each other, we'll call them rarefactions. So this is how a sound is produced by a vibrating source. Vibration is necessary in order to produce the sound. All right, now we have to discuss about the nature of the sound waves. All right, so I have already described about the compressions and the rarefactions. When the disturbed particles are close to each other, they are called the compressions, and when the disturbed particles are away from each other, they are called the rarefactions. Now let's discuss the type of the sound wave. Like, what is the type of the sound wave? So the type of sound wave. Which type of wave is it? Which type of wave sound is? So the sound waves are longitudinal in nature. We have already discussed the longitudinal waves. So the light waves were the transverse waves, and the sound waves are the longitudinal waves. So in the longitudinal waves, the direction of vibration, let's suppose some object is vibrating in the horizontal direction. This is the direction of vibration of any object, and a wave will also produce in the same direction parallel to the direction of vibration. So that is the direction of wave. All right, so this is the direction of wave, and this is the direction of vibration, and that's the direction of wave. Okay, so in such cases, the waves that are produced, they are called the longitudinal wave, and in those longitudinal waves we see the compressions and rarefactions. So those longitudinal waves have compressions and rarefactions. Now I'm going to draw a wave over here so that I will show you how the compressions and rarefactions look like. Okay, so let me just draw a wave over here in order to show you how the compressions and rarefactions look like. So let me just draw a wave. Here's the wave. You see the cycle. Some cycles are close to each other, and some cycles are away from each other. Again, they'll become close to each other and they'll go away from each other. So you see over here, this area, these are the compressions. This is due to the compression, and this area over here, that is due to the rarefactions. So when the wave particles are close to each other, when the particles are close to each other, we'll call that region as the compression, and when they're away from each other, we'll call that region as rarefaction. Okay, so that is the nature of the longitudinal wave. Now we will discuss about the range of frequencies that are audible to the humans. So the range of frequency that the human can hear. Okay, so audible range of frequencies. Audible range of frequency for humans. So the humans can hear the frequencies from 20 hertz all the way to 20,000 hertz or 20 kilohertz. So all the sounds that are in between this range are audible to the humans. Okay, some animals may hear the sound above or below this frequency range, but the sound waves that are in between this range, they're audible to the humans. Okay, now we will discuss about the travel of the sound waves in the vacuum, or let me put it this way, we'll discuss why the sound waves are not able to travel in the vacuum. So for that purpose, let me just clear it up. Okay, so the question is why the sound waves do not travel in vacuum. The reason is simple. In vacuum, there are no particles. In air, we see the particles, like the air particles, the molecules. But in vacuum, we do not have any particles. So whenever we have a vibrating source, let's suppose we put a speaker over here, which is the vibrating source. So that's the speaker, and it is producing the sound wave. But you see over here, there's nothing. There are no particles. So whatever disturbance this speaker will cause will not affect the region surrounding it, because there are no air particles. So that's why the sound waves are unable to travel in the vacuum. That's a simple reason. Okay, now we have to discuss about some features of the sound wave, where we will relate the frequency, amplitude with the loudness and pitch. Okay, so we'll discuss the relationship between frequency, amplitude, loudness, and pitch. So over here, let me just draw a wave first of all. So I'll explain from there. So let's suppose I have a wave. So that's the wave. Let me just draw two waves, in fact, so I can compare. Here you go, the first wave, then the second wave, then the third wave over here, so it'll be like and the fourth one over here. There you go. Okay, Now let's discuss them one by one. But before discussing that, let me just tell you about the features of a wave, that is frequency and amplitude. First of all, let's discuss the amplitude. So amplitude is basically the distance of this cycle, the maximum distance from the mean position. So this is the amplitude. How high the cycle is, how much away the minimum or the maximum point of the wave from the mean position, or how much is the distance between the crest or trough from the mean position. So over here, this distance over here is the amplitude. The distance of the maximum or the minimum point from the mean position is the amplitude. Now frequency. So frequency is basically, it is the number of cycles passing through a point in 1 second. So if the cycles are close to each other, the frequency will be higher. If the cycle is taking more time, the frequency is lower. Okay, now let me just explain you what is a cycle. So for this wave, the cycle is starting from here, from this position. It goes to the positive maximum, then back to 0. Negative maximum, back to 0. So from here to here, one cycle has been completed. Okay, now look at this. It has taken this much of time. Now let's compare it with this cycle. From 0 to positive maximum, back to 0, towards negative maximum, back to 0. Now this has taken more time. So since this has taken more time, so it has less frequency, and this cycle has taken less time, so it has more frequency. So that's the only difference. That's how we compare the cycles of different waves. Now, loudness and the pitch. So loudness has direct relation with the amplitude, and the frequency has direct relationship with the pitch. So loudness and amplitude are related to each other, and frequency and pitch, they are related to each other. More amplitude means more louder wave, more louder sound. More frequency means the pitch will be high. Okay, so let's compare these cycles 1, 2, 3, and 4. Now look at this one. Let's compare these two cycles first of all. So this cycle has high amplitude, this cycle has low amplitude. I'll say that the frequencies are almost same. So the loudness of this cycle, this wave, is more as compared to this one. Okay, similarly, let's compare these two waves. Now look at this. This cycle is completing quickly, and this cycle is completing after some time. So this wave has high frequency as compared to this wave. Similarly, let's this cycle has, yeah, that's correct. Now let's compare the amplitude. Now look at the distance from the mean position. So the distance of this wave from the mean position is over here, 1 unit you can say, and the distance from the mean position of this wave is 3 units. 1, 2, 3. So this wave has more amplitude and this one has lower amplitude. So we will say that the loudness of this wave is greater. Why? Because the amplitude is greater. And the pitch of this wave is greater. Why? Because the frequency is bigger. Do you get it? So that's how we'll compare the amplitude, frequency, loudness, and pitch. Now I'm gonna discuss the other waves over here. Now for this one, it has high amplitude, this one has lower amplitude. All the frequency is almost same. So this wave will be louder, this sound will be less louder. So loudness will be higher over here and lower will be over here. And here frequency will be higher over here and frequency will be lower over here. So frequency is directly related to the pitch and amplitude is directly related to the loudness. Okay, now we'll discuss about the echo or the reflection of sound. How an echo is produced, we'll discuss that now. Okay, echo. Okay, for example, you clap over here. At this point, you make a clap. Okay, and over here there's a wall. Let me just draw a straight line. There's a wall here. That's the wall. Now what will happen? The sound will go over here. It will travel in this direction, and after reflecting from the wall, it comes over here. Now, for example, you place a mic at this position. This is the mic. When you clap, the mic will hear the first sound. Okay. When this sound will go and hit the wall and comes back, the mic will hear the second sound. Second sound. Now this second sound will be considered as the echo for this sound. Okay, so why this echo has happened? This echo has happened due to the reflection of the sound wave. Wherever this was the source of the sound went in that direction, it hit the wall and came back and was detected at the mic, and the mic detected the second sound. So that second sound will be considered as the echo. Now, what if we have to measure the speed of the sound by using this technology, or by using this experiment? We can measure the speed of sound by using this experiment. How? Just measure the distance. Just measure the distance from this source to the wall. Okay. Once you know the distance over here, let's suppose this distance is 10 meters. You'll put the mic over here and start the clap. So when the clap happens, the mic will detect the first sound. You'll note down the time. So let's suppose the time was 0 seconds. The sound will travel towards the wall. It hits the wall and come back, and the mic will hear the second sound. Let's suppose the mic heard the second sound after 300 milliseconds. Now look at the distance that the sound has traveled. The sound has traveled a distance of 10 meters from the clap towards the wall, another 12 meters from the wall towards the clap. So the total distance that the sound has traveled is 20 meters, and the time is 300 milliseconds. You can just convert that into the seconds. That will be equal to 0.3 seconds. Then you can use the famous distance equals to speed multiplied by time formula to measure the speed of the sound. So the speed of the sound will become equal to 20 times 0.3. Whatever is the answer will be the speed of sound. So by this experiment, you can easily measure the speed of the sound, and usually the speed of the sound in air varies from 300 millimeters per second to 350 meters per second. Let me just write it somewhere. So the speed of sound in air varies from 300 to 350 meters per second. Okay, so that's how you will measure the speed of the sound in air. I'm talking about the air. I'm not talking about the liquid, solids, or any other thing. Vacuum, the sound does not travel in vacuum. It only travels in air, liquid, or solid. There must be something to vibrate. If there's nothing to for carrying the vibrations, it means the sound cannot travel. Okay, now let's discuss how the sound travels in the solid, liquid, and gases. So how how the speed of the sound varies in solid, liquid, and gases. It all depends on the distance between the particles. As you know, like in solids, let me just give an example of solid. This is solid. The particles in solids are tightly packed with each other and they're very close to each other. So these are the particles in the solid. They're tightly packed and they're very close to each other. Now let's take the example of the liquids. In the liquids, the particles are at the moderate distances from each other. One particle is here, another is here, other is here, like that. So the particles are at the moderate distances from each other. They're not tightly packed and they're not like in definite order. Now let's talk about the gases. So in the gases, the particles are away from each other. They're too much away from each other. One particle is here, other one is here, one is here, other one is here, like that. So that's the nature of particles in solid, liquid, and gases. Now, in order to understand the speed of sound, how the speed of sound varies in the solid, liquid, and gases, we have to check how close the particles are from each other. So as you can see over here, in the solids, the particles are tightly packed. So when you vibrate something over here, when there's some vibration over here, all the particles will vibrate and they will transfer energy from one particle to another pretty quickly. So the speed of the sound will be fastest in the solids. Similarly, if you put a source of vibration on the liquid particles will vibrate, but they will take some time to transfer that vibration from one particle to another. So the speed of sound in liquid will be lesser than the solids. But let's talk about the gases or air. So this particle will vibrate, it transfers energy to other particle, then this particle transfers energy to the other particles, like that. So they will take some time to transfer energy from one particle to the other particles. So they will travel slower than the liquids. Okay, so the speed of the sound in solid, liquid, and gases, they depend wholly on the positions of the particles in the solids, liquid, and the gases. Since the particles in the solids are close to each other, so the sound will travel faster. In the liquids, the particles are like a bit away from each other, the sound will travel like a bit slower. And in gases, of course, the particles are away from each other, so the sound will travel at the slowest speed possible. But in vacuum, since there are no particles, so the sound will never travel. So let me just draw the comparison of the speed of sound in solid, liquid, and gases. So the comparison is over here. In solid, the speed of sound is maximum, then liquids, and in the liquid, the speed of sound is bigger than the gases. So this is the comparison. The speed of sound is maximum in solid, and then comes the liquid, then comes the gases. Got it? So that was about the speed of sound. Now we have to discuss about the another type of sound waves which have higher frequencies. For example, the frequency is bigger than the audible frequency range, and that is ultrasound. So ultrasounds, as the name suggests, these type of sound waves have the frequency bigger than the audible frequency range. So I'll write it over here. The sound waves having frequency higher than the audible frequency range, which is 20 kilohertz or 20,000 hertz. So the frequencies having the sound waves having the frequencies bigger than 20,000 hertz, they are called the ultrasound waves. Okay, so we cannot hear the ultrasound waves because they're beyond the audible frequency range, but we can use the ultrasound waves in different applications. Ultrasound waves have different applications. For example, ultrasound waves, it is used for prenatal scanning. I'll just write it over here, some uses of ultrasounds. So I'll just write it over here, uses. So the first use is the prenatal scanning. So ultrasound waves are used to scan the baby in the womb of a mother. So you send some ultrasound waves, and then those sound waves are reflected from the baby, and they are detected at the remote at basically a transducer of the ultrasound. So in this way you can scan the baby, and you can know the medical condition of a baby in the womb of a mother. Okay, so that's the first use and the most common use of the ultrasound waves. And the next one is to measure the depth of the ocean. So we use the ultrasound wave to measure the ocean depth. So for example, there's a ship. Let's suppose the ship is here. Let me just draw somewhere here. Okay, so let's suppose there's a ship. The ship is over here, just like a normal design. Now this is the okay, there's the ocean, there you go, and this is the ocean bed. So ultrasound waves will go like that. It will reach the bottom of the ocean, and from here they reflect back like that. They will reflect back, and it will be detected at the ship. So let's suppose okay, from this point where the ultrasound wave was sent, let's suppose the time was 0 second, and we know the speed of the ultrasound wave in liquid. So let's suppose the speed of the sound in liquid, let's suppose it's because it's more than air, so let's suppose it's 400 meters per second. That's the speed. And when this reflected wave will be detected at the ship, let's suppose the time will be 4 seconds. After 4 seconds it will be detected. Okay, so we'll just measure this 400 meter with 4 seconds, and we will get to know the distance, but that distance will be to and fro while going down and coming up. We will divide that distance by 2, so we'll get the actual depth of the ocean. I hope you got it. So this is another use of the ultrasound waves in measuring the depth of the ocean. So these are the two uses. There are other uses as well, but I'm just restricting because it's not it's not a very important topic, you can say, or main topic. So I think this will be enough. The rest of the stuff will rest of the application we'll discuss in when we'll do the past papers. So this is it for the sound waves. I hope you got it, and if you have any question, you can just comment below, and I'll respond as soon as possible. Thanks a lot.